Hi, welcome to the video on electron configuration using the periodic table. So at this point you should already have the notes down. You should have your periodic table labeled with the different blocks S, P, D, and F. I've also put in here the elements that we're going to be that you have in your practice so that it's just more convenient when writing electron configurations. Okay, so let's go ahead and get started. So for these example problems, the first sort of divided. Part 1 contained just neutral elements that can be from any of the blocks S, P, D, or F, although we don't focus on F, so it's just going to be from S, P, or D blocks. Then we have ions, but these are just main group ions, so ions that are found in S and P blocks, and then transition metal cations, so cations meaning they have a positive charge and they're found in D block. All right, let's take a look at, and we'll just go through a couple examples in each section. And for each example, we're going to do a full configuration and a noble gas configuration, electron configuration, and we're going to determine the number of valence electrons. Okay, we'll start with aluminum. So the first step, as you recall, is to find the element in the periodic table. And here is aluminum. And once you find the element in the periodic table, you're going to use that to write the last part of the electron configuration. So how do we get the last part of the electron configuration? So the format works this way. The energy or shell number of the last part of the configuration will correspond to the period that it's in. So aluminum is in the third period. So the first number we would write is 3. And then the subshell will depend on the block it's in, so it's in P block, so it's going to be 3P. And then the number of electrons is how many times I have to count over in that block. And since it's in the first group in that block, I'm only counting over once, so there's 3P1. So that's what aluminum ends with. So I'm just going to write that here. And now what I'll do is I'll fill in the rest of the electron configuration. So for the full configuration, starting with, I'll start with the 1s2, all right, since I'm writing full configuration, and when I do noble gas, I'll show you what we'll start with. All right, so I'm trying to write my electron configuration going all the way to 3p1, so that's going to be 1s2, 2s2, 2p6, 3s2, and 3p1. All right, so I end there. Now, of course, you can use the periodic table to figure out the electron configuration because it's sort of organized in that way as you go from left to right and then snake back around. So this will be 1s2, 2s2, 2p6, because there's 6 of those in the P block, and it's in the second row, 3s2, and then 3p1. So you could do it that way as well. All right, so now that I have my full electron configuration, let's get the noble gas configuration. So for the noble gas, you follow the first 2 steps are the same. So again, you find your element and you figure out what the last part of the electron configuration is based on the period it's in and what block it's in. But instead of starting at 1s2, you're going to start with the previous noble gas. That means the noble gas in the row or period above your element. So aluminum is here. In the third period, I'm going to use the noble gas in the second period, which is neon. And I'm going to write that in brackets, and that's where I'm going to start my electron configuration. So I'm going to write neon. And then I'm starting here at neon, and now I want to go to the next period, right? So this would be 3s2 and 3p1. And the reason why this works is because the electron configuration for neon is 1s2, 2s2, 2p6. So I've already taken care of that by writing neon in brackets. Okay. All right. So let's do one more example, and then I'll show you how to do the noble gases for these. We're going to do zirconium, which is here. Okay. So for it's in the D block. So remember, the D block has some exceptions, so you always want to be extra careful with the D block. All right, so then my first step is to identify where the element is. It's here. And then I need to figure out what the end electron configuration is. So notice that zirconium is in the 5th period, all right? But because it's in the D block, remember the D blocks, that energy shell will be 1 less than the period number. So we sort of noted that here. The shell number for the D subshells are always 1 less, okay? And F would be 2 less, all right? So this is actually, even though it's in the 5th period, these are 4Ds, all right? So I'm going to write my end configuration as 4D, and I count over 1, 2, so 4D2. So even though it's in the 5th period, it's 4Ds because the Ds are 1 less than the period number, since they get shifted down to the 4s being slightly higher, for example, than the 3ds. Slightly lower in energy than the 3ds. All right, so now we go ahead and we can do our thing here, and we go 1s2, 2s2, 2p6, 3s2, the next is 3p6, all right? Now we get to 4s2, and remember, after the 4s's, then comes the 3ds, and we fill up 10 of them. And then now it's back to the 4p's, so now we're back in 4. Then we go to 5s2, and then 4d2. Okay? All right, so again, you can fill it up by, if you remember the pattern, what the pattern's like, you can fill it up that way, or you can fill it up using the sort of snaking method electron configuration in the periodic table. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. All right, and now we'll do our noble gas configuration for this. So once again, I find the noble gas in the period or row above it. So zirconium's in the 5th period. I need to use the noble gas in the 4th period. That's krypton. I'm going to write that in brackets. And then what I have to fill in is the rest. I've taken care of all of this part of the electron configuration up until the 4p6s. So now I'm up to the 5s2, 4d2. Okay. All right, so now I want to show you how to do the valence electrons. For valence electron configuration, what you're going to do is, for most things, what you do is you look for the highest energy level. So in this electron configuration, the highest energy level is the 3rd energy level or 3rd shell. And that's the coefficient in front. So you look for that highest number, and I'm going to underline those. Then you're going to count up the electrons in that shell. Because remember, the valence shell is the outermost shell, so it will be the highest energy level shell for the most part. So we're looking for how many electrons are in that 3rd shell. So you find the highest energy shell. So in this example, it's the 3rd shell. So you find the highest coefficient, 3rd shell, and then you add up the electrons in there, and that's 2 plus 1. So you add up the exponents. And that will give us 3 valence electrons. You can also do the same thing for the noble gas configurations. And in fact, for the noble gas configurations, it's easier because it will be what's after the noble gas. All right, so that's for most things. You do that sort of thing for S and P block. D blocks, transition metals, are a little different. For their valence electrons, what you have to consider is you have to consider that the valence electron transition metals are the highest energy S and D. So for transition metals, you look for S and D, not the highest energy number per se, but the highest energy S and D. So here, in this case, the highest energy S will be the 5s, and the highest energy D will be the 4D. And so we add up those two numbers, 2 plus 2, gives us 4 valence electrons. Oops, okay. All right, so for transition metals, look for S and D. For everything else, you just look for the highest energy shells and add up the electrons. Let's do let's do a few more examples, couple more examples with ions. So we'll start with this. Make sure you modify in your paper. It's germanium, GE, not GA. And the process is the same pretty much, except for we have to account for if you see a positive or negative charge here, if you have an ion, you'll have to remove or add electrons respectively. So if it's a positive charge, like this is +2, I'm going to have to remove 2 electrons. If it's a negative charge, like this is -2 minus, I'm going to have to add 2 electrons. Okay, so I'm going to start off on doing the same thing. I'm going to find the element in the periodic table and to get the end configuration. So here's germanium. It's in the 4p2. It ends in 4p2. So I'm going to write that down. Now, because it's a +2 charge, I have to subtract 2 electrons. All right, so whatever the charge is, you're going to do the opposite to get the number of electrons. If it's +2, you'll subtract 2. And that cancels out completely the 4p2. So that means that that is completely gone. So now what I can do is I can write my electron configuration up until whatever's right before the 4p's, which would be the 3d's. All right, so I do 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d10. So again, I was ending here if it was neutral, but because it's +2 charge, I'm ending over here, and that would be the 3d10. All right, and then for the noble gas configuration, of course, you would find the noble gas previous to it, which would be argon, and then fill in the rest of the configuration. So argon is in brackets, and then after argon, I'm going to have 4s2, 3d10. And you can see that here. So here's where argon is. So to fill in the rest of the configuration, I have to do 4s2 and then the 3d10. All right, so that's that. If we were doing it for an anion like phosphorus, so here's phosphorus. Its electron configurations is in 3p, 1, 2, 3, so 3p3. But because it's a -2 charge or 2 minus charge, I'm going to add 2 electrons to that. And so this now becomes 3p5 is where it ends. So I write my electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. And with it being 3p5, so here is where phosphorus is. That means I have the electron configuration of the element here, which is chlorine. And that means it's isoelectronic. If they have the same electron configuration, it's isoelectronic to chlorine. Iso meaning the same. All right, so now we're going to do our noble gas configuration. The previous noble gas to phosphorus is neon. And then I fill in the rest, which would be 3s2, 3p5. Okay, valence electrons for these are pretty simple. These are all main groups, so again, just look for the highest energy. So here it's 4. The highest energy is in the 4th shell. So that means that germanium 2+ only has 2 valence electrons. This is not a transition metal, so I'm not including the Ds. I'm only focusing on the highest energy shell. If it was a transition metal, I would use the Ds. But since germanium is not, we'll just do the 4s. All right. Then the same thing for phosphorus. I look for the highest energy shell, which is the 3rd shell. And again, I know it's the highest energy because it has the largest coefficient, right? Add those together, 2 + 5. So I add up my exponents to get the number of electrons or valence electrons there, and there we go, 7. All right, last examples we're going to go over are the transition metal cations. So for transition metal cations, it's a little bit different because what you want to do is instead of subtracting just like normal the number of electrons or adding the number of electrons, I guess for cations we're always subtracting. So instead of just subtracting the number of electrons from the highest energy, we're going to remove them starting with the highest energy S and then remove from the D. Okay, so what I like to do is I like to have the neutral configuration and just remove that way. So let's go ahead and do it for rhenium. This will be the one example we do. For this, so let's start with writing the end configuration for rhenium. Rhenium is in the 6th period, and so that would correspond to 5D. 1, 2, 3, 4, 5. So I'm going to write the last two subshells there. The 6s, so I'm going to write my s's because I got to remove from those first, so that would be 6s2, and then 5d, 1, 2, 3, 4, 5. Okay, now since it's a +2 charge, I have to remove 2 electrons, and I'm going to remove them from the 6s. I'm going to remove from the s first. And when I do that, when I remove 2 electrons from the 6s, since there's only 2 electrons there, that gets rid of it. So now all I'm left with is 5d5. All right, and so now I can go ahead and fill in the electron configuration for rhenium, which is actually a pretty long one since it's in the 6th period. So the electron configuration will go like this: 1s2, 2s2, 2p6, 3s2, 3p6. And remember, we go to the 4s's, 4s2, then to the 3ds, 3d10, and then 4p6. And then we go to the 5s's, 5s2, then we go to the 4ds, 4d10, and back to the 5p's, 5p6. All right, and now once we get to the 6th period, 6th and 7th period, we have to be careful because our F blocks start to insert in there. So when we fill this up, we're going to fill up the 6s2, then we fill up the 14f's, and then we go back and fill up the 5d's. Now remember, in our case, we've gotten rid of the 6s2 because it's rhenium cation, but if this was neutral rhenium, we would include that. So I'm not going to write the 6s2 because we've gotten rid of it because it's a cation, but if it was neutral, we would fill that in. So then after where the 6s's are, we're going to put the 6s2s, we would put in our 4f's. Remember, for the F block, it's 2 less than the period. So if this is a 6th period, it will be 4f. So then we do 4f14, and then finally 5d5. It's a lot, right, for our electron configuration. Okay, so that is the electron configuration for rhenium 2+, and then our noble gas configuration would be, we find rhenium, the previous noble gas is xenon, and what we need to fill in there is everything after xenon, which we've gotten rid of the 6s2s because of the cation, but we'll fill in the 4f14 and the 5d5. So I put xenon in brackets, 4f14, 5d5. Now the last thing is to get the number of valence electrons. So again, for transition metals, you'll focus on the S and D. We've gotten rid of our S's. All we have are the 5d5, so that means we have 5 valence electrons here. Okay. All right, so that is it for this video. You can sort of check your answers using the answer key, but I hope you found this helpful. Alrighty, folks, good luck with your work. Have a quality day.